Right now, across the globe, artificial intelligence is generating complex video from scratch. Supercomputers are running massive climate simulations, and millions of people are simultaneously exploring expansive, high-fidelity video game worlds. Underneath all of this activity is a single piece of silicon. It's a specialized chip that was originally engineered for the narrow purpose of drawing pixels on a screen. What began as a tool for digital entertainment became the physical foundation for modern scientific research, autonomous vehicles, and deep learning. To understand that shift, we have to look at the specific mathematical bottleneck that forced this technology into existence. In the early days of computing, a machine's processor, the CPU, was responsible for every task: calculations, inputs, and running programs. A CPU is a highly intelligent, complex piece of engineering, and it handled the simple text displays of the era perfectly. But then graphical user interfaces and arcade games changed the requirements. Suddenly, computers needed to output thousands, and eventually millions, of pixels to a screen, and they had to do it dozens of times every single second. That demand exposed a limitation in hardware. Drawing millions of individual pixels isn't an intelligence problem, it's a repetition problem. Asking a brilliant general-purpose CPU to manually color in millions of tiny squares one by one wastes its capabilities. The entire digital world needed a specialist. This specialist is the Graphics Processing Unit, or GPU. Think of the difference between a CPU and a GPU like a math test. A CPU is a single mathematician solving complicated equations. A GPU is an army of average students. The mathematician works one by one, but the army finishes instantly, solving everything at the exact same time. This is the core of parallel processing. The realization that thousands of simple cores could work together simultaneously completely changed the direction of modern computing. To see parallel processing in action, look at how a modern game landscape renders. For every frame, the computer answers a checklist of mathematical questions. What color is this point? Where is the light coming from? Should there be a reflection here? These questions must be answered for millions of independent pixels. To keep the image smooth, the hardware recalculates all of them 60 times every second. Instead of tackling that list in order, the GPU divides the screen into thousands of tiny sectors. It assigns its army of cores to calculate the lighting and color for all of those sectors concurrently. Photorealistic graphics are the result of this synchronized division of labor. The GPU isn't drawing pixels one after another, it's drawing all of them at once. This assembly line is the graphics pipeline. It follows a specific 6-step process. First, geometry processing and transformation. The GPU maps 3D mathematical shapes, polygons, into a spatial grid to determine their precise position in the digital world. Then, lighting and rasterization. The hardware calculates how light bounces off shapes, flattening 3D objects into a 2D map of pixelated squares. Finally, pixel shading and final frame. Colors are assigned to every square, pushing the finished image to your monitor. This entire pipeline executes from start to finish in a matter of milliseconds. However, thousands of fast cores are only useful if the data can reach them. If the processors are constantly waiting for textures to arrive from the main system, the entire process stalls. As this diagram shows, it's like a high-speed factory. If workers have to travel across a city for materials, production drops. GPUs solve this with VRAM, or Video Random Access Memory. It acts as a dedicated storage warehouse located right on the factory floor, holding the textures and models the cores need. Because VRAM is physically close to the cores, the data path is instant. The processors pull what they need the moment they need it. For years, the gaming industry drove the evolution of this hardware. Demand for realism forced manufacturers to scale up the raw power and memory of their chips. Eventually, researchers realized that the math used to render lighting and shadows is identical to the math required for complex scientific simulations. Soon, graphics chips were predicting weather, modeling complex molecular physics, and analyzing vast scientific data. The GPU had transitioned from a consumer product for entertainment into a necessary tool for the modern scientific laboratory. This adoption set the stage for the rise of artificial intelligence. Training an AI model requires billions of calculations happening in unison to adjust the weights of a neural network. A deep neural network relies on a web of nodes processing data simultaneously. This matches the parallel structure the GPU perfected for gaming. As this diagram illustrates, the hardware architecture and the software model are structurally equivalent. The rapid expansion of AI capabilities was only possible because of this accidental hardware acceptation. Software innovation found its perfect engine in a chip built for video games. Today, NVIDIA, AMD, and Intel are locked in a competition to build the baseline hardware for the next century of computing. This technology is currently discovering new medicines, rendering movies, and processing the sensor data that keeps autonomous vehicles on the road. Most people will never see a GPU at work, but the world relies on its results. The tools that shape our future often function as invisible systems, working silently behind our screens to build the digital world.